Are there any questions on the WebEx? No? Okay. So Mohan, thanks a lot again. Thanks for talking to us remotely. Okay, give a big hand.
Okay. Thank you. Bye.
Okay. So the next 45 minutes, we have 4 short talks. So these are some of the talks by the students. We include them like these are either just been accepted or in the pipeline or just will be presented. So that these are very fresh from the press kind of thing. So it will be presented by Gautam, who is a PhD student. Also Nick, he will give 2 talks. And then we have one more, I think, Chanchun, right? So let's go one after another. And then I think there are a few announcements. 5 o'clock, I think we'll be going to the SOC tour. So I think, all right, is it 5 o'clock? 5 o'clock. So whoever is the coordinator, I think as soon as we finish this, they can assemble and go. And then we'll have the reception at 6:30. So we'll also show you the direction that is very close to the hotel. So let's keep on moving. So Gautam will be presenting some of the very latest things, what we have evaluated our MHAPIS Plus on SDSC. There is a Cosmos system they just deployed. It is a MI300A AMD GPUs. So we have optimized MHAPIS Plus on that. So why don't we get started, Gautam? Yeah.
Hello. Yeah. Hi, everyone. Today I'll be talking about the performance evaluation and optimization of MHAPIS Plus on SDSC Cosmos system. So first of all, I would like to thank SDSC for providing us the early access to the system. And then I also like to thank C1 for helping me build the slides. Okay, so I'll be starting with the introduction. So we'll be quickly discussing what's new with this architecture and all. And then we'll go deeply into the APU architecture. Then I'll show a bunch of performance evaluation numbers, and then I'll conclude the talk. So let's quickly go back to the old days and see where it all started. So Subemi cluster was the first GPU powered cluster, which has both CPUs and GPUs back in 2008. And then soon after later, like in 2012, Titan proved that this kind of model works best, and it became the top 1 in top 500 systems. And then, but then the issue was like at that time, the interconnect between a CPU and GPU was always a PCIe. Soon after later, recently NVIDIA introduced this new architecture called Grace Hopper architecture, where the CPU and GPU are both tightly coupled using NVLink. And ALPS is the first supercomputer to introduce this. And then now we currently have El Capitan, which is the top 1 supercomputer system, and it is powered by AMD MI300A APUs. So let's see what is the current model challenges. So I call it as a 2-island problem. So the issue is, so here we have 2 different islands. One is CPU island and the other one is GPU island, and it has their own memory spaces. So connected by a bridge, or they're connected by some kind of means, but they don't have a common unified memory that both CPU and GPU can access. So because of that, the data must be manually copied from a CPU buffer, CPU memory space to a GPU. And then because there involves some kind of a transfer, it consumes, it causes some latency as well as some energy, which reduces the overall efficiency, right? Then I think the industry started working on it, and NVIDIA introduced NVLink and AMD introduced Infinity Fabric to make this bridge faster, but then the bridge still exists and the data copying is still there. Like we need to copy the data from CPU memory to the GPU memory, but it's just that it's faster now. But then with this model, it creates some burden on both the software as well as the developers or the programmers, because they have to explicitly manage the data movement as well as the synchronization. So this results in higher code complexity as well as longer development time and also some performance trade-offs. this brings to MI300A APU architecture. So AMD introduced this, and it is the first data center APU, accelerated processing unit, which integrates both the CPU as well as GPU cores within a single package. So it has x86 CPU cores and CDNA3 architecture GPU compute units. So it also comes with a shared coherent memory pool, which is a HBM3 memory, which is a very fast memory. So this eliminates the explicit host to device transfers because both the CPU as well as GPU cores can access the same physical memory seamlessly. So because of this, our new architecture, the communication cost, and it changes everything, right? So the communication cost changes, and also middleware strategies need to be changed because this is a completely new architecture which was not explored before. Sorry. Yeah. So MI300A is based on a chiplet-based architecture. So it has 3 core complex dies, which is also called CCDs, and each CCD has like 8 Gen 4 CPU cores of total 24 cores for one APU. And then we have like 6 accelerated complex dies, which is also called XCDs, which is basically a GPU, which is basically a GPU compute units. So a total of 228 GPU compute units are available on one APU. And then we also have something called IO die, which act as basically a interposer for all these fabrics or all these chips. And also this architecture has, this MI300A APU has 256 MB of infinity cache, and it provides a peak theoretical bandwidth of 117.2 terabytes using this infinity cache. So you can see the pointer. Okay, so on the left bottom, you can see the LO link, which connects the XCD as well as the AMD Infinity Fabric. That gives you like a 17.2 terabytes aggregate. And then we also have like 8 physical stacks of HBM3 memories, which are spread across all the 4 IO dies, of total giving you like 128 GB. And the theoretical peak bandwidth for this HBM memory is 5.3 up to 5.3 terabytes per second. Okay, do you have any questions up to here? If not, we'll go to I'll quickly talk about the SDSC Cosmos architecture. So it has total of 42 nodes. Each node is equipped with 4 APUs of total 168 APUs in the system. And each node, within the node, there are 4 APUs, and all of them are tightly connected using AMD's Infinity Fabrics, which is also called XGMI interconnect. So this interconnect provides a aggregate bandwidth of 768 gigabytes per second, and also 256 peer-to-peer AP2APU bidirectional bandwidth between the APUs. And this has and every node comes with 4 HP Grace Slingshot 11 interconnects, offering a bidirectional bandwidth of 200 gigabytes or 25 gigabytes per link in each direction. So I'll be quickly showing some performance evaluation numbers. So this is intranode point-to-point numbers using CPU buffers. As you can see that with latest MWPitch Plus, we are comparing against the system MPI library, which is CrayMPitch. As you can see that we at 4 kilobytes, message says MWPitch Plus provides improvement of 31%. And similarly, it's also resonated even in the bandwidth. We are getting the similar benefits even in the bandwidth. Coming to the internode, so we saw that the internode, the bottleneck for the internode is the slingshot, which should give us like a 25 gigabytes per second, and we are achieving that bandwidth over here at 4 MB or even at 512 kilobytes. So these are GPU intranode numbers. So again, in the GPU intranode numbers, at medium to large scale, we are so MWPitch Plus is either comparable or doing better than CrayMPitch. Similarly to the bandwidth, either the MO pitch plus is comparing either equal or better than the Cray pitch over here for medium to large message sizes. And then going to the internode, again, the MO pitch plus and Cray pitch perform very similar. MO pitch plus gives like a little bit better numbers at certain ranges, like 256 bytes. We are getting like 3% improvement. And now the interesting part is the collectives. So I'll be showing both the intranode collectives as well as multi-node collectives. So this system has 192 threads. So as you can see that from all gather, so these are all CPU collectives. So you can see that with all gather, we are getting almost 437% improvement compared to Cray pitch. And then for all radios, the peak improvement that we got is like 108% compared to Cray pitch. Going further, all-to-all also produced like 347% peak improvement compared to Cray pitch. And if we go to a 16 node, 64 PPN CPU based collectives, we are seeing an improvement of 130% improvement at 1 kilobyte message size. And then for all radios, we are seeing around 34% improvement at 1 kilobyte message size. So in the interest of time, I'm quickly show some more numbers. So these are these are intranode GPU collective. So we can see that like even at the GPUs, with the GPU buffers, we are seeing a significant improvement from 77% to 195% for all gather, and from around 200% to 400% for all reduced collective and intranode with 4 APUs. It has 4 APUs in one node. And again, coming to all, we see around 76% peak improvement to 387% peak improvement at 16 kilobytes. And for radios, again, we see like around 200% improvement compared to Cray pitch. So this is 8-node GPU collectives. Again, we see like good improvement numbers. I'll quickly switch to full scale. So we also have 32-node 4 PPN numbers, which is like the maximum that we can get on this machine. So at this scale, for all gather, we are seeing around 13% improvement, and also at 16 kilobytes, it's around 800 improvement for all gather. And for all radios, again, we are seeing very good improvement at 32 kilobytes, which is around like 240% improvement compared to a Cray pitch. Again, the same story with the all-to-all. So we are winning by a huge margin, around a 200% improvement compared to Cray pitch. And yeah, so that concludes. So in conclusion, so MI300A has like integrates both CPU as well as GPU cores together, and it has access to the same unified shared memory. So this brings us, this opens a new research direction as well. Yeah, if you have any questions, please feel free to ask.
Any quick questions for Gautam? Anything on the online? Okay, if not, let's give thanks to Gautam. We'll switch to the second short talk. It will be presented by Nick. He's also a PhD student working in the group, especially working on the compression, on the line compression, on the fly compression, as we discussed earlier, and also FPGA based, bringing MPI to FPGA. So today you'll be talking. So you'll have 2 talks in this session. So this one will be on extension to issue micro benchmarks for collective compression error measurement. Go ahead. Yeah.
All right. I think you guys can hear me.
This one you need to share.
Do I do that or do they do that? I think this is this folder, but this one. This isn't the right presentation, right?
Thank you. All right. Hi, everyone. I'm Nick Contini. I'm here to present a work from a previous master's student who's now graduated, Jacob Pfizer. I'm going to be talking about evaluating error of compression-based MPI operations. Yeah, I think you guys already heard it talk about compression, but what's compression used for? It's for reducing data volume. Traditionally, we kind of thought of it more as being used for reducing the size of data before writing it to disk, but a previous student of ours, Xinghua Zhou, he decided to apply compression to communication and had designed point-to-point and collective protocols for reducing the data using compression, communicating the data, and then decompressing on the other side. So, ultimately, we're trying to reduce data volume with compression, and where you get the most data volume reduction is with lossy compression. So that there are lossless methods out there, but the compression ratios do not generally compare to these lossy compression techniques. Now, of course, it's in the name, lossy compression introduces error. So, that can create an issue for those that are, creating scientific applications. In the AI space, it's been well studied that a lack of precision can mostly be a benefit due to performance, and you won't suffer that much from the accuracy loss. But for scientific computation, that there's some more exploration to be done there. So that kind of motivates this work, which is, we have the OSU micro benchmarks. We have a way to measure latency, bandwidth. We even already had validation in OMB, but now we need kind of an extension of validation. We don't need a binary, is it correct or is it incorrect? We need a, how close are we to, correct is sort of what we need at the end of the day. So, we want to provide a way for scientists to develop their applications, utilize our compression-based communication, and evaluate whether or not the compression introduces too much loss, or if at the end of the day it's negligible. And ideally, this is also used to further integrate more compression solutions, so that way application developers can choose between their different compression techniques and see which one fits their data the best, because ultimately the effectiveness of the compression is dependent on the data, and the data will vary on an application to application basis. So that's essentially what we're proposing here, an extension to OSU micro benchmarks. We first, kind of the first step is, what are the measurements that we want to provide, the different metrics for accuracy. There isn't just one. How do we give users the ability to specify what the communication data looks like? Currently in OMB, there is no way of doing that, right? It's either an empty buffer or it's a buffer with a rather simple pattern for the sake of simple binary validation, right? And lastly, we'll show some results that kind of show how the data changes accuracy based on, in an all-to-all compression scenario. So what are the metrics that we decided to include? We kind of decided to bring kind of your classics like absolute mean error, mean squared error, mean relative error. These are generally, I think most people in the room here would understand those. They're very simple to calculate. They're very simple to understand. One that maybe is less familiar to some people is the peak signal to noise ratio. And this can kind of, in short, be considered the quality of a signal after being processed, right? So it's very popular in the compression community. If you read compression papers, you'll often see this metric, and so that's kind of why that's in here. So when you see this peak signal to noise ratio metric, essentially higher is better. It's the opposite of these other three, where low is better. On top of providing mean measurements, we also provide min and max, because perhaps your application is very dependent on all values of your buffer being within a certain threshold. So if, if for some reason 10% error on this single element is catastrophic, we provide a way for you to know that, rather than just having a mean across the whole buffer. And of course, we would be open to any suggestions. Different fields of study have different measurements of error. We would be open to suggestions for adding new measurements to OMB. So then, this is arguably the most important part of this work, is how do you specify the data that we are going to communicate and measure? We provide two different ways to do this. So if you know how to model your data using a random distribution, we actually have built in a way for you to specify a JSON format, you can see it there at the bottom, to generate random values based on a certain distribution. And where this inspiration comes from is there is a paper detailing that the training weights in deep learning generally follow a Gaussian distribution. It's a sparse Gaussian distribution. So if you know how to model your communication data using a random distribution, this can be quite convenient, right? You don't have to actually pull your data from your application and give it to OMB. However, if you do need to feed it real data from your application, we provide a way to just have a custom data set where you can provide a binary format. So you can, if you like, run your application, export the contents of a send buffer to a file, and then you can use that in OMB, use it across different runs, switch compression methods, and see how the accuracy is affected. So for the sake of time, I'll speed up a little bit here, but there is a challenge in providing all this still, in that how the MPI standard doesn't have a way to specify whether or not compression should be used in an operation. So ultimately, Jake had to work around this. We can't run all-to-all and assume that compression is not running, and then run all-to-all again and assume that it did run and do the comparison. So what we decided to do instead is to use files as essentially a communication substrate. Have one buffer construct the data, write it to a disk. All ranks can read the data and know what's in the send buffers of each rank, and then construct what the receive buffers in each rank should look like. And then that can be used as a way to measure the error. And that's kind of just like a visualization of what that looks like. So you can see at the bottom, the rank 0 is kind of simulating what the collective will do and constructing the expected receive buffer. So here's just some numbers, what these numbers might look like if you were to use MPI all-to-all with ZFP compression using Evapage Plus. You can see here, this is actually like a good demonstration of why the different metrics are important. You can see here that uniform random distribution is performing quite well on the mean absolute error metric. And that's essentially because ZFP is a zero suppression compression algorithm. So it's able to easily normalize the values from the distribution and remove the zeros. However, if you look at PSNR, it's a different story. Uniform actually has the worst performance. And that's because, essentially the absolute errors maybe being a little bit misleading. The general shape of the signal is actually still being retained in the exponential case. It's just that the signal itself tends to have higher magnitude values. And so then here you have a demonstration of relative max error. You can see, in some situations, there's very, very low relative error. But then you see these spikes where, maybe your application is not as resilient against these levels of error. And finally, we also have a way to kind of specify the level of sparsity of the data. And you can see that in general here, the more sparse the data, the better the compression performs, which again is related to the zero suppression. So in conclusion, we will be releasing these into OMB soon. We would love to use this as a way to co-design your applications with compression-based communication. And in the future, we'd like to provide support for more operations, compare across different compression algorithms, and characterize applications to come up with the best practices. So.
Thank you. Let's thanks, Nate. I think we can quickly move to the other two presentations, and then if you have any questions, we'll have enough time in the reception time and all to discuss.
The tours.
Yeah, so for the tours, 5 o'clock?
Yeah, we're going to start meeting.
Yeah, so he's the coordinator. So those who want to leave for the tour around 5 o'clock, we'll finish and then you just go and then follow him. Okay. So let's go with the next presentation by Chen Chun. He's also a PhD student and working on all these optimizing collectives on the GPUs. So Matt, somebody can help here. See I think that it's not coming.
Is it done? Oh.
Okay, I think let's close the files. Yeah.
Did that make it worse? Okay, I just got it over. Okay. Is your first one? Is it this one? Oh.
Okay. Just go to the first one. Okay.
Okay, so good morning, everyone. I'm Chen Chun. So I'm going to present our recent work, design and optimization of GPU with MPI or reduce using direct send receive communication. So we'll start with introduction, motivation, and discuss the implementation, and go through the evaluation results, and conclude by conclusion of future work. So first, so everybody must be familiar with MPI or reduce, and we know that MPI reduce is like everywhere. For example, in HPC application, Ember, it uses or reduce communication for medium message, and for AI application like PyTorch, in this DDP framework model, you use or reduce from like medium message to large message, like at the mega level to the gigabyte level. So what's wrong here? So it's because the reduce at scale remain challenges. So we can look into this figure. So it's a bandwidth figure. So we want to get higher bandwidth, so reach the top like 25 gigabyte per second. And we test like 2 different algorithms. So the red ones are the ring algorithm and the blue one are the RD algorithm. But different lines means that the scales are different. So it's like 16, 32, and 64. So if we just look into the ring algorithm, the 3, and it's obviously like as the scale goes up, then it's really hard to get the top like bandwidth. And if we compare these 2 different algorithms, it remains a gap in the middle message size here. So that's where we want to figure out like how to propose a solution for this or reduce gap in the medium message sizes. So this is our implementation. So we look into the previous algorithm. So typically we use or reduce RSA algorithm, which means we have reduce getter first and then or getter first. And in this algorithm, we use the ring algorithm. And in ring algorithm, there are several iterations, depends on how many rank you have. So if you have more process, more rank, then you have more iterations. And in each iterations, the message size will be going to be, divided into chunks. And the chunks have no dependency. So with a higher number of ranks, then the message chunk will be getting smaller. So that's what we see, that as the messages go higher, then the gap go obvious. So we propose a direct send receive algorithm. So in this algorithm, we can just gather the message from different ranks at the same time. So here's an example. And in example, we divide the concurrence send and receive code into 2 batches. So there are going to be 2 steps. In the first step, we're going to gather the message like here. And in the second batch, we're going to gather the message from here. And once we got the message, we store the message in the temp buffer. And after we got all the message, we're going to do the reduction kernel, real reduction kernel, and then store the data back to the receive buffer. And we have like 2 optimizations for that. The first one is overlapping, and the second one is kernel fusion strategy. So in previous read algorithm, there are data dependency, but in this one, there are no. So we can use the low overlapping technique to overlap the communication and computation in between different batches. And we also can apply the kernel fusion strategy to combine the kernel together. So you're going to reduce the data write operations to the GPU buffer. And let's look into the evaluation. So we conduct the evaluations on 3 different machines. The first one is Vista. So there's one Grace Hopper 200 GPUs and with the infinite band. And second one is Cardinal. And there are 4 GPUs, NVIDIA GPUs, and 4 infinite band HCAs. And the third one is Data AI. So similar configuration, but with Slingshot. And if we look into the benchmark level evaluation on Vista, so at 64 megabytes, we can see that we outperformed the previous MPI RD algorithm by 64%. And we also outperformed Nickels by 9%. And on Cardinal nodes, similar for large message, we reached like 18% performance gain from MPI RSA algorithm. And in certain message, like here in 8 megabyte, we are outperforming Nickels by 37%. And similar trends on Delta AI. And we also have the results on application level. So the first one is the deep learning application, Nano GPT. So on Vista, we get like 7% improvement compared to MPI stack. And on Cardinal, we get 2.5% improvement compared to Nickel. And in HPC application, Amber, so in this 4 different workload, we get like 27 to like 9% improvement. Yeah, so conclusion. So we propose a direct send receive or reduce algorithm. We see good numbers in both benchmark level and application level. And those features are already released in the latest MRPG Plus 4.1 RC. And in the future, we're going to extend this designs to together or reduce together. Yeah, that's all I have. Thank you.
So we'll go to the final talk. So Nick again will present. Extended screen. Okay.
All right, I'm back. So I'm Nick Contini. I'm here to present my work. This is actually a debut of my SC25 paper. I'm going to be discussing how to design communication for data flow centric acceleration. So we've heard the same song and dance in these recent years. Moore's law is slowing. Dennard scale is ending, and that means we need to innovate on the architectural side of things. No doubling in frequency every couple of years. So one flavor of this exploration, this architectural exploration, is a subcategory called data flow architectures. And the emphasis is on moving away from von Neumann-like architectures where data is moved from the memory hierarchy to a compute unit and then back to the memory hierarchy. And instead, we, in data flow architectures, they focus on having the data quite literally flow from one compute unit to the next, or at least from one compute unit to something like a first in, first out buffer, or you know, this gives benefits in the sense that you're spending less time idling for waiting for data to arrive. You can implement finer grained parallelism. And a lot of these architectures tend to be application specific. So you end up with a slimmer architecture that also, you know, reduces the amount of energy and power to execute the application. And you know, when you have all this custom data flow, you also are able to optimize performance for applications with irregular memory access, rather than suffering from the cache thrashing that you might experience in a more generic processor. So this is just like an example of like what a data flow architecture would look like. If you're looking at me and don't know what I'm talking about, you would start down here at the DRAM. The data would flow up into the FIFOs at the top, and the FIFOs feed into processing elements. And instead of those processing elements outputting back to DRAM, they flow into more FIFOs, which then flow into more PEs before being written back to DRAM. So then this brings up the question, well, what about scale? A lot of data flow architecture works focus on simply optimizing the single accelerator case. So there are some works that focus on implementing distributed communication between FPGAs. A lot of these solutions have issues with flexibility, such as like in the direct network case. It's very like application specific, or it won't be able to reach scale out. Some of these situations where you implement indirect networking protocol on an FPGA, they can be very expensive. Implementing TCP IP can actually take up a significant amount of chip resources. So that's also kind of unideal. Also, you know, say you want to send your data from something like an FPGA or a custom data accelerator to a GPU. A lot of these solutions don't have the flexibility to implement that. So now you might be thinking, hey, here's Dr. Panda's student talking about communication. Maybe we should look towards MPI. Well, one of the issues with MPI is that it follows this compute then communicate model, which is not that sort of fine-grained streaming communication that we're looking for in data flow acceleration. But we still want the benefits of MPI. We still, it's, the de facto solution for high performance scale out communication. So can we find a middle ground here? And that's what this slide says. Can we provide a communication interface that enables scale out on data flow architectures? Can we make it easy to use? And can we integrate it into existing HPC applications? So the solution I decided to take was to actually offload the communication to the host processor. So instead of trying to implement all the networking on the accelerator itself and use chip resources, I instead decided maybe we just need a fine-grained data transfer mechanism between the accelerator and the host. That saves us chip resources. Another key part of this is providing a streaming interface. So generally, I do a lot of my work in the high-level synthesis space. That's a very, useful tool, development flow for quickly developing hardware, and a lot of researchers have started to embrace that. So we wanted to provide HLS MPIs with a streaming interface with the benefits of MPI, but with slightly different semantics. So this is the API that I ended up coming up with. It's I call it collective streams. And you can see where, if you're familiar with HLS, you can see how this does kind of look like a hybridization of stream interfaces for HLS as well as MPI. The general flow is if you're writing your C++ HLS kernel, you construct your collective stream and you start an operation, whether it be send, receive, or a collective like broadcast. Each end of the collective stream will be connected to different compute units. So if you have a compute unit that's producing send data, you will call write on the collective stream. If you are developing a compute unit that is receiving communication data, you call read on the other end after calling start. And there's some other neat little things such as, if you're doing something like a bcast, which is a one-to-many operation, the send, right? If you write to one end of the collective stream, it will actually loop back to the receive end on the same accelerator. So what does all this actually look like when it's implemented? So if you look off here to the right, you see that we've got 2 compute units. That's essentially the application from our point of view. And everything to the right of that is kind of what's behind the scenes of the collective stream. You have a transaction manager that's in charge of communicating metadata. It kind of orchestrates between the other collective stream modules as well as the host processor. It informs the host processor, hey, we're about to do broadcast, for example. And you have your other 2 modules that are essentially responsible for pushing or pulling data. So if you're sending out data, it gets pushed to a ring buffer and host memory, and that is what that host memory, that is the buffer that you are essentially communicating out of here. And the kind of dirty little secret here is we're actually still using MPI here. We actually do an MPI call on the ring buffer to communicate the data. On the receiving end, this MPI operation will output the data into a incoming ring buffer, and that will be pulled in by the data pooler, and then the application CU can read in that data. So you might be, at this point in the talk, be asking, well, okay, how does this actually get applied? Where can we actually use it? So this is kind of the test case I had in my, the case study I had in my paper, where we took an existing LinPack implementation on FPGAs, and we decided to optimize it. So if you know the LinPack algorithm, there's kind of there's 4 different kind of kernels that you can break the computation into. You have your LU factorization, and the output of the LU factorization is broadcasted rightward and downward in the process grid. You do an update on the top and left block rows, and those results are broadcasted inward. So we have 2 different broadcasting steps. Now, if you use kind of the compute then communicate model, you kind of miss out on this overlap because in most accelerator-driven computations, there's no way for the host to know data is available until the kernel ceases to run. So this synchronization between the host and the accelerator prevents this overlap. So what if we try to, develop a data flow-centric version of LinPack? Well, you kind of get the top figure here. And this one looks very simple, right? All these, right, the LU factorization unit and the 2 block update units are directly connected through a streaming interface. And as data is computed, it can immediately be sent to the next CU. However, there's nothing here, there's no networking hardware here, right? There's no way to use the compute units on the other accelerators, right? So that's why we integrated our solution, which is the bottom diagram, where we put our collective streams in, and where you see those double arrows is there's this implied broadcast. So one accelerator will be computing data in its LU compute unit, and once it hits that double arrow, a broadcast will occur, and all accelerators running this architecture will then have the data, the output of the LU, and those will be fed to the block updating units, which in turn will then be broadcast again through another collective stream. So ultimately, that ended up and getting us benefit. So if you look at the top, you see increased throughput from 18, 14, 11% for 4, 9, and 16 accelerators respectively. If you inspect just the portion of the application that we optimized and look at the latency, you see the bottom graph, where you see a 5 to 29, 19, and 11% improvement for 1, 4, 9, and 16 FPGAs respectively. And all of this comes from that overlap of communication and computation, as well as the reduced kernel launches needed, right? To a certain extent, you only needed multiple kernel launches for that host accelerator synchronization. But if you don't need that synchronization anymore, we'll just do one kernel launch, and now you don't waste that kind of driver overhead of launching kernels. And so, I'd like to remind you guys, this is only like a little bite-sized portion of my talk. So please look forward to, seeing the extended version at SC25. But, for future work, I would be very interested in maybe providing the same interface from the GPU side of things. So that way you can integrate, data flow acceleration with this embarrassingly parallel acceleration, utilizing different networks, like using direct networks that are directly attached to the accelerators, kind of akin to NVLink in conjunction with the host network, which is essentially what we're discussing here, and exploration with more applications. In the paper, we discussed LinPack and Sensor micro applications, but there could be further use cases in graph computation or AI applications. So, and that's my talk. So thank you.
Okay, so I think we'll close the conference today now. It has been a long day, but so I think there is those who are going to the tour, so please go. There is a shuttle which will take you back to the hotel, and then 6:30 we'll meet at the reception, which is very close. You will see from the map. I think around. Is there a map here? I think we had the intro slides. It's just a walking distance, and. Can you go back to the reception map? I think it is there, or just 1 minute. Intro slides, intro day 1. And we have very nice food, drinks. There is some trivia, games, prizes. So please come. Okay, don't skip this. The last one, I think, yeah, here, this one. Yeah, so just from the hotel, I think, where is the hotel? I think there. So just walk down 2 blocks here, and then go this way. You will be able to just plug in the map as address. And then tomorrow we'll be starting at a little bit 10 minutes earlier. Tomorrow we have a long day. 8:20 we'll be starting. Okay? Yeah. Which one? Yeah, the shuttle will be there like at 5:15, I believe. So you can take back, and tomorrow morning also there will be shuttles back. Okay? Thank you. Thanks a lot to all people today. Yeah, around that area you need to stop.
Okay, I'll see you. Where does this need to go?
I think just give it back.
Just bring it up.
Yeah.
Thank you. I just want to say I'm in Ohio now. I arrived 2 days ago.
Okay.
So
Nice seeing you in person. Yeah.
I'm still settling in, but that's why I was late today. But I'll be here tomorrow.
Okay. So you're coming to the reception.